So we're talking about how glaciers move, and we identified different mechanisms of movement, including internal deformation or creep, subglacial deformation, and basal slip or sliding. I want to say a little bit now about internal deformation or creep. Ice deforms in response to applied stress by a variety of different mechanisms that relate to the atomic structure and the mechanical properties of ice. You can read about those in the textbook. What I want to do is look at how those relate to the bigger scale of glacier movement and then to the morphology and overall dynamics of glaciers and ice sheets. And to do that, I want to start thinking about Glen's flow law, which is a relationship between applied force, stress, and resulting deformation, strain, that was based on some experiments done by John Glen in the 1950s. Glen's flow law you've probably encountered before. E equals A times tau to the power n, and n is often given as a 3. E, well, that's the amount of deformation. That is the strain, or from our point of view for today, the creep of ice that we're interested in explaining. And that creep, that deformation, is given by a function of tau, which is the applied force, the stress. Now, it's an exponent of that, so it isn't just an even progression of a little bit more stress, a little bit more strain. The stress is going as the cube, the strain is going as the cube of the stress. So if you increase the stress a little bit, you'll increase the strain a lot. The other term in here is a strength or resistance term, and that's the hardness of the ice, which is largely temperature dependent. Other factors affect it as well, such as chemical impurities and so on, but it's basically a temperature dependent hardness parameter that determines the resistance to the applied force. So we have some applied force, we have resistance or strength in opposition to that force, and based on the relationship between those two, we end up with strain or deformation. In other words, as in so many things in physical geography, the amount of movement, the amount of strain, depends both on the applied force, the stress, and also on the strength or resistance, hardness parameter, within the material. So step one of our understanding is to say that the strain depends on the stress. The next question obviously then is, well, what determines the stress? So E equals A times tau to the n. The strain, the deformation, the creep is a function of the applied force, the stress. Well, where does that stress come from? And that's where we call in our second equation. I said earlier on in the course that we were just going to have two equations that would crop up quite a lot and be quite important. Glen's flow law is one of them. The other one is the shear stress equation. And the shear stress equation tells us what tau, what the stress is. And tau is rho GH, which is essentially the weight of ice above a point that we're interested in, because rho is the density of ice, G is the force of gravity, and H is the thickness of the ice above our point. So the shear stress is a function of the weight multiplied by the sine of alpha, a function of the gradient driving the movement. So for some packet of ice in a glacier or ice sheet, we can say that the shear stress affecting that ice is a function of h, the height or thickness, the force of gravity, the density of ice, which gives us the weight, and then the sine of this gradient alpha, which is the surface gradient of the ice. Now, before we carry on with this topic in the next video, I want you to do your first bit of very basic ice sheet modelling for me. You've got your two equations, E equals A times tau to the n and tau equals rho GH sine alpha. You know the situation we're dealing with, so what I want is for you to come up with three graphs for me. Each one is a graph against depth through the glacier of the shear stress all the way from the surface to the bed, and from that the strain rate all the way from the surface to the bed, and from those the velocity of the ice all the way from the surface to the bed. So I want you to draw lines on each of these graphs that illustrate for me the stress profile, vertical stress profile, the vertical strain profile, and the vertical velocity profile. That's your challenge. Take some time over that, have a think about it, and I'll come back in the next session and we'll carry on talking about glacier creep, internal deformation. We'll also move on and start talking about glacier sliding soon. But first of all, just see if you can figure out for yourselves what I'm going to say about these three graphs in the next session.